Hello everyone! I'm presenting our paper Conformal Performance Range Prediction for Segmentation Output Quality Control. My name is Anna Wundram, and I want to talk to you about segmentation, which is a popular application in the medical domain, and recent models are achieving great performance on a number of problems, and are thereby relieving experts of time-consuming work. One of these problems is blood vessel segmentation in the retina, where good segmentation results can be achieved. However, even the best segmentation models can fail. There might be images that are difficult to segment, for example, because of the disease they display. In these cases, the model output should not be used for downstream tasks. This is where we need quality control. In these situations, we do not care about the quality of the input image, but only about the quality of the model's output. As long as the model is able to segment the image, it's all good. But how can we control quality? We predict a performance measure, for example, the DICE score. Based on the DICE score, we could then set a threshold for the minimum performance required to pass the quality check. These metrics can be directly computed from the softmax output of the model. I would like to refer to the paper for details. But they are only accurate if the model is calibrated, which modern neural networks rarely are. This is where our work comes in. Instead of a point estimate, we predict a performance range, leveraging the uncertainty of probabilistic models. We can then also guarantee that the true performance lies within that range with the user-set probability by applying conformal prediction. We follow three simple steps. First, we estimate the DICE score from the softmax outputs. Second, we use sampling-based probabilistic models to predict a heuristic performance range, so lower and an upper bound. And then we apply conformal prediction to turn the heuristic uncertainty from the models into rigorous ones, and therefore obtain statistical guarantees that the ground truth performance is within the predicted performance range with a certain probability. To give you an idea of what this looks like, I would like to present the qualitative results on the test set. We compare 5 different commonly used probabilistic models, remember, to obtain the performance estimation ranges. Each value on the x-axis represents one image. The scattered points denote the predicted DICE, and their color indicates the quality of the image. The better I align the scatter points with the ground truth DICE line in black, the better the performance prediction. The gray shaded area shows the predicted range. Nearly all models achieve the marginal coverage at the user-set probability of 90%. Marginal coverage means that for a random test point, the true DICE is included within the bounds. We notice that the size of the predicted performance range correlates with the ground truth DICE and the quality of the image, meaning that the size of the performance range is expressive of the actual uncertainty underlying the input image. All models were able to predict the performance with low absolute errors. Of course, we also evaluated the segmentation performance. I would like to refer to the paper for more details on this. As previously mentioned, nearly all models achieved the marginal coverage at the user-set probability of 90%, which is the blue dashed line. A more expressive metric is the conditional coverage, so the coverage conditioned on the size of the predicted performance range. This shows how expressive the bounds and therefore the underlying uncertainty measure is. For example, very large intervals cover a range of 0.5. This could include an estimated range from 0.4 to 0.9 or 0.1 to 0.6. For all ranges that fall within that category, we compute the coverage. This is then repeated for all 4 size categories. In that aspect, Fischer performs best. Now lastly, assuming coverage is fulfilled, smaller intervals are desirable. Overly large interval sizes can mean poor DICE estimation or poor uncertainty estimation. Coverage can always trivially be fulfilled by predicting very large performance ranges. In order to be useful, the performance ranges must be as small as possible while still fulfilling the coverage. Here again, Fischer overall produces the smallest intervals. The ensemble does not produce any of the small intervals or tighter bounds. This is indicated by the missing scatter points close to 0. Summing up, performance prediction point estimates may be insufficient for robust quality control because of suboptimal calibration of neural networks nowadays and high performance uncertainty in low-quality images. This is why we combine sampling-based uncertainty quantification methods and split conformal prediction to predict performance ranges with a statistical guarantee. For future work, I would like to point out the comparison of this approach to input quality control methods. If you enjoyed this short insight into our work, please come to our oral presentation at the Unshow workshop on the 10th of October. I will see you in Morocco.